All right, it's time to go ahead and begin. All right, so today we're going to do several things. The lecture is going to be long today, probably at least 90 minutes, maybe a little longer. So we'll take a break about halfway through or so. But the assignment for today is going to be hardware number 4. Okay, and that's building 2 more pieces of the Otter. Okay, two more pieces of hardware. The ALU, which stands for Arithmetic Logic Unit, and the immediate generator. So I'm going to start talking about both of these kind of from a high level point of view, and then come back from them and talk more specifically about what you need to do in Verilog or System Verilog to do the modeling. And where we're going to spend most of our time is tracing the data path and also what the control signals are for these 5 instructions. And then there's an activity, after the lecture part, and before you start hardware number 4, there'll be an activity that's a group activity. We'll make each table a group where I'll have you do the data path and control signals for 2 other instructions. And you see, being able to trace how the data progresses through the Otter, along with what the control signals have to be, is very important when we get to the point where you'll design the control unit. Okay, remember we've been talking about how the control FSM outputs all the different read and writes, and the control unit decoder outputs all the signals for the select line of the muxes. Well, in order to code what you need to code for that control unit, both the FSM and the decoder, you need to know what the data path and what the control signals are for each signal. So remember we talked about real instructions and pseudo instructions. You remember what the difference is between the 2? Like, what do we mean by real instruction as opposed to pseudo instruction? That's something Right, exactly. Yeah, the pseudo instruction can be made up of multiple real instructions, or it can also be also a single real instruction just with particular values. But the key thing is the first thing you said, where real instructions is what actually gets processed by the processor. Okay, so you'll need a data path and control signal diagram for each of the real instructions, because if your Otter can execute all the real instructions, then it can do all the pseudo instructions too. Okay, so I think I might have only mentioned this one time, like at the very beginning of the course, maybe the first day. Does anyone remember approximately how many real instructions there are? I mean, if you look at all the instructions, there's probably like around 60 real or total instructions. So, if you count the pseudo instructions along with the real instructions, it's probably around 60 or so. But do you know how many of all those instructions are real instructions? Like approximately 16. How many? 16. Actually, more than that. Anyone else want to take a guess?
My next guess is like 24.
A little bit more than that too.
25, 48.
You're getting closer.
30.
Yeah, it's around 30 or so.
That was my first guess.
I think when I counted one time, I got like 36, and then another time I counted like 34. So I don't know if I, accidentally counted some pseudo instructions, but there's around 30. Maybe a little bit more than that, but there's definitely at least 30. Okay, so that means 30 diagrams, showing the data and also the control signals, that you'll have to come up with, in order to do that control unit. And we're not going to design a control unit until after the midterm, so it's still a few weeks away. But, in my opinion, it's better to do, some of these diagrams a little at a time, as opposed to trying to do all 30 all at once when you absolutely need it. So, we'll do some today in class, we'll do some on Thursday, okay, next class. And then after the midterm, there'll be another lecture where you'll do a few more. Okay. All right. So we're gonna start with the ALU, again, stands for Arithmetic Logic Unit. So what do you think this piece of hardware does?
I'm guessing it does all the arithmetic
And logic, exactly.
and logic.
Any Jeopardy fans out there? Any people that watch Jeopardy? Nobody watches Jeopardy anymore? Is that because Alex Trebek is no longer the host? Or nobody ever watched it? Well, if you ever watch Jeopardy, you'll see that sometimes they have a category, and the category is stupid answers to stupid questions, where the answer is right in the question. So, you know, that could be in that category, right? What does an ALU, an arithmetic logic unit? Well, it does arithmetic and logic. Okay. And when you design this, you want to design it as one MUX, okay, a single MUX. And you designed a MUX as part of the program count, right? So what kind of statement did you use to model this in Verilog? Case statements, right, a case statement. So for this ALU, you want to do the same thing. You want to use a single case statement. You do not want to use an if statement, okay? And I'll explain the reason why a little later, because after we go through this diagram, seeing how the data flows, you know, I'll come back and explain why we want it as a single MUX, okay? Made up of case statement. Okay, so now here's the select line of this MUX that's going to be the ALU. And notice it's this ALU fund. Where is ALU fund coming from? Like each bench has an otter diagram. Where is that coming from? What's producing the ALU fund?
The control unit decoder.
Right, control unit decoder, right? And I think I've mentioned several times previously, right? That all the select inputs are coming from the control unit decoder. And notice it's 4 bits. And this table has all the operations that the ALU performs. See, there's addition, subtraction, or, and so on. So why is this 4 bits? Why not 3 bits or 5 bits or some other number of bits? Why is it 4 bits? Yeah, exactly. See, we have 11 operations here. So the minimum number of bits we need is 4, right? Because how many values can we represent with 4 bits? 16, which is the closest to 11 without being under, right? Because if we only had 3 bits, we could only represent 8 values and we wouldn't have enough for 11 things, right? If we had more than 4 bits, that's just more bits than what we need. Okay. Now, I will come back to this towards the end after we go through that diagram and talk more about, you know, what you need from your Verilog experience or Verilog knowledge in order to do this. All right. So we're not finished with that. You'll also design an immediate generator. Now, in this class, what do we mean by immediate? Because you've seen immediates in instructions. Well, a jump is either a branch or a jump. But what's an immediate? Like when you see immediate in a instruction? Yeah, it's just a number, right? Immediate just means a constant. So this is the piece of hardware that's going to generate that number, that immediate that's in our instructions. And it turns out there's 5 different immediates. You type, I type, S type, E type, and J type. And everyone should have this page from the assembler manual, and it shows the format of all the different immediate types. So there's, did you have a question? Or? So there's 5 immediate types. And what's nice about this is that all these immediate values, they're generated in parallel. Okay, so you know what this means? Because, you know, in circuits, you learn about things that are in series and you learn about things in parallel. What's like a distinguishing feature between something in parallel and something in series?
Something in parallel will be happening at the same time as the other thing.
Exactly, right? If you have something in series, like this has to happen before this happens, right? And this has to happen before the next thing happens. But if things are in parallel, they're all there all the time and they're available always, right? So what this means, since these different type of mediates are being generated in parallel, is that in your system Verilog, you can just use assign statements, right? Because assign statements are continually happening. So the code that you're going to write for this immediate generator is just going to be 5 assignment statements. 5 assignments. You'll have an assignment for U type, an assignment for I type, and assignment for the 3 others. And if you take a look at this handout that shows how each immediate is formatted, well, you'll have a number of bits that's attached to some other bits that's attached to some other bits. And in CP133, at least some of you, maybe not all of you, but at least some of you have probably learned in Verilog how to do concatenation. You remember that term, concatenation? Like, what does that mean? In Verilog, if you concatenate something, what are you doing? Yeah, it's like you're taking smaller amount of bits and attaching them to other smaller amount of bits and making a bigger number of bits. Okay. So we'll come back to this, after we go through this diagram, and we'll talk more about what you need from your CP133 in order to, generate these immediates. You're going to see that you need concatenation, replication is really handy, and also like parsing of bits. You get something that's 32 bits and you only want like say 5 of those 32 bits. Okay, so again, we'll come back to this and talk about it in a little bit more detail later on. But for the next probably hour or so, although we'll take a break, is we're going to come up with the data path and also what the control signals have to be for the 5 instructions. Okay, and then I'm going to have you do 2 instructions as an activity. So we're going to start with this instruction here. Okay, so what is this instruction doing? Now, for this part of the class, it would be handy to have your instruction manual, where the instructions are. So you can look at these instructions that we're talking about. I don't know, did anyone make a hard copy of the manual? Am I the only one that likes hard copies? Use a tablet. All you young people, of course, you like looking at screens, but I'm old, so. Well, that's not the detail. That's like a brief listing. It's better to have the full description. Yeah. So who can tell me what this instruction does? Okay, it subtracts. Subtracts x20 from x10 and stores in x1. All right, right. It's going to take the contents of one register, subtract from it the contents of another register, and then put the results in a register. So which one of these registers is the destination register where the result is going to be put? Okay. Yeah, so this is our destination register. Right? And then we have 2 source registers, one source 1, the other one source 2. So which one's source 1? Next time. Okay, this is source 1. So this has to be source 2. Okay. All right, so now, and I'm going to be using blue for control and red for data. And by the way, on Canvas, for each of these instructions I'm doing in class, I have the result. I have the end product that we're going to figure out here, both the end data path and the end control signal. So it's not that you have to copy this all down here in class. I mean, if you want to, that's fine. But, you can always check and see if you missed something by just comparing it to what I already have on Canvas. Okay. All right. So where we're going to start by tracing how the data flows is we're going to start here at the output of the program counter. What do we have at the output of the program counter? What is the program counter providing us? Address of what? The instruction to be executed. Okay. So you see right here, we have the address instruction to be executed. Okay, so that's where we're starting. And then the output of that program counter, it goes to this input of our memory module, this address 1 input. Now, what's inside, or what do we have here at this memory module. Right, and remember how it's segmented, right? The memory portion is segmented. So what segment do the instructions go in? What is that segment called? The code segment. Right, so we get the code segment. You know, then we got, what else do we have? The data. There's a data segment that we haven't really talked about yet, but we will eventually. Then we have a stack, which again, we'll talk about eventually towards the end of the quarter, okay? But here's where our instructions are. They're in the code section, okay? Okay, so look what we have here. At the output of the program counter, it's 32 bits, right? It's a 32-bit address. Here, at this input, address 1 of the memory module, we're taking 14 of those 32 bits. We're only taking 14. And those 14 are 2 to 15, right? The second bit to the 15 bit, that's the 14 bits. So first of all, why are there only 14 bits? Why aren't we using all 32 bits?
The 14 there includes definitions of registers and units, and we just want the actual instruction itself and the other stuff.
Well,
That's it again.
okay, well, a good guess, but yeah, the instruction is the whole 32 bits. Okay, so, and this is the address of the instruction, remember. Okay, this isn't the actual instruction yet. This is just the address of where the instruction is. So, you know, like we talked about, you know, the first instruction of every program is at address 0, right? So, you know, at reset, this would be 0. And we're starting at the first instruction at address 0. Okay, so that's not the reason that, excuse me, that's not the reason that we're using just these 14, excuse me, just these 14 bits. Let me ask you this, because this might help you with the answer here. How many values can we represent with 14 bits?
A lot.
Okay, a lot, that's true, but more specific than a lot. 2 to the 14th, which is, now you want to know a little trick, because this is how, when we get into the teens of bits, this is how I figure out how many values. See, I just remember that 2 to the 10 is 1K. Right, or again, 1K, excuse me, I got like something stuck in my throat here. 1K to base 2 is 1,024. Let me take a wig of water here. I had some lasagna before class, and some of that avocado cheese getting stuck in my throat here or something. Okay, sorry. Okay. So back here with the 14 bits. So see, I remember 10 bits, we can represent 1,024, right? Which is 1K in the digital world. Well, every time you add a bit, you double the number of values that you can represent with that number. So you see, if I add one more bit, right, now I have 11, I can represent 2K bits. Right, 2 to the 12, 4K. 2 to the 13, 8K. 2 to the 14, 16K.
Is that just like an approximation, like it's that?
Right, because the exact would be like for 2K, you would take 2 times 1,024. Yeah. So yeah, well, it's just understood when you're talking digital that when you say K, you mean 1,024.
Yeah.
Right, because if you take 2 and you raise it to the power of 10, it comes out to 1,024, not 1K. Okay. Okay, so with 14 bits, we can represent 16K different things. Well, do you remember there was something about the code segment that involved 16K? Because we figured it out in an earlier class. You remember what that 16K was? Do you remember what the address of the code segment is? Like, where does it start? Because where's the first instruction? What address? 0. Right, so all zeros, that's where your first instruction is. But do you remember what the top address of the code segment is? Very good, yeah, it's 0, 0, 0, 0, 5, Yeah, yeah. And if you figure out how many addresses you have within this range, it's 64K. But then remember, how is this memory addressed? Like, byte addressable, right? Each byte has an address. So this is 64K bytes, but if you want to know how many word instructions you have or how many instructions you have, it's 64K divided by 4, which is 16K. So you see this 16K, that's the maximum amount of instructions that you can have in your code segment. Okay, so you see that's why we're only taking 14 of the 32 bits, because we only have 16K instructions max. Now notice that we don't take bits 0 and 1. In fact, again, Dr. Hummel designed this memory module. Okay, so I gotta give credit where credit is due. And I haven't looked at this in too much detail, but I'm pretty sure what Dr. Hummel did is he made bit 0 and bit 1, he just made them equal to 0. And he just made bit 0 and bit 1 of this address for the instruction 0. Why do you think he did that?
Because of those last two values, if it's not a 0, it's not divisible by 4, so it's not the first instruction or the first line.
Well, you got it when you said when either one of those values aren't 0, it's not divisible by 4. But we know how are these instructions separated in address? By 4, right? In fact, I mean, that's why you got the +4 here, because again, each instruction is 32 bits. The memory is byte addressable, right? So each instruction address is a word address, and word addresses are separated by 4. Okay, so you see, that's why you don't see the bit 0 and 1 here, because in the module, they just made 0, because we know instructions are separated by 4. You're never going to have an instruction with an address of 1 or 2 or 3 or any other number that's not divisible by 4. Okay? All right, so we have our instruction address here. Okay, now we want to get the instruction at that address here at the output of this module, DL1. So how do we make that happen? What does the value of this read enable have to be? A 1, right? It's active high, so that would have to be a 1. So then when we get the edge of the clock, now the instruction that's at this address is going to be here at the output. Right? So at the output DL1, we're going to have our instruction to be executed. Right, so we're going to have the machine code of this instruction, right? The machine code that you can see in the description and manual, that's what's going to be here. Okay, now in this instruction, we have these 3 registers. So the data, right? The machine code for that instruction is going to flow here. 5 bits is going to go here because that's our address for source 1. 5 bits here, right? Because we need an address for source 2. And 5 bits here because we need an address for the destination register, right? What we're going to write to. Now, this is also connected, right? The output of the memory module is also connected to our immediate generator. But this instruction doesn't have an immediate. So even though there's going to be data here, right? There's going to be these 32 bits. We're not going to use it because that instruction doesn't have an immediate, doesn't need an immediate to be generated. Okay? So what is the data going to be right here on this address 1 input? Like what number is going to be there? 10. Right? Because how many registers are inside the reg file? 32. Are they byte addressable? No. So each register has its own address, right? Register 0 is going to have address 0. Register 1 is going to have address 1. Register 2 is going to have address 2, and so on, all the way up to register 31. That's why it's 5 bits, exactly, right? Because with 5 bits, you can represent 32 things, right? 0 to 31. That's all we need for this. So on that input address 1, you're going to have the address of source 1. So there's going to be a 10 here. Okay, what's gonna be on address 2? What data? 20. What data is gonna be on the right address input? 5, because that's our destination register. Okay, now, you designed this reg file, and when you designed it, how did you, well, what's a better way to phrase it? These outputs here, which we're reading, right? We're reading the data in the registers to these outputs. Did you make them asynchronous or synchronous? Async. So as soon as those addresses, right, address 1 and address 2 are here at the inputs, at the outputs, we're gonna have the contents of those registers. So here at RS1, we're gonna have the contents of register 10. Okay, so that's what I mean by that X10. That's contents of register 10. And then here at RS2, we're gonna have the contents of register 20. Okay, the contents of register 10, that data is gonna go to this mux, the 0 input of that mux. And then this data from register 20, it's gonna go to this 0 input of this bottom mux. Okay, these muxes determine what goes into the ALU. ALU source, that's the select line to this mux. So what does this value have to be to get this data to the ALU? A 0, right? Because that's how muxes work, right? You put a 0 here, it's going to connect the data on the 0 input to the output, which is going to go into input A, source A of our ALU. How about this select line here? What does it have to be? 0. Okay, so that's the data from register 20 is going to be at the other input of the ALU. And then the ALU is what does the subtraction. Okay, so the subtraction is going to happen inside the ALU. It's going to be, again, a single mux. And then the result of your subtraction is going to be at the output. Oh, one other thing we forgot though. What makes this subtraction happen? What are you pointing at? What I'm pointing at, right? This select line is going to choose what operation takes place, right? We have these 11 operations, and it's ALU fun that determines which of these operations is performed on inputs A and B. So in order for a subtract, we need what? Yeah, we need a binary 8, 1 0 0 0 for an ALU fun. All right, so the fact that ALU fun is 1 0 0 0, that's what makes the subtraction happen, right? It chooses that operation from the 11 that are available. So now we have the result of our subtraction at the output of the ALU, and it goes to this mux. Okay, this mux that attaches to this input of the reg file, WD. What does WD stand for?
Right.
Right, write data, because the result, that's what we want to write to our destination register. So what does this select have to equal? 3. Okay, that will connect input 3 to the output of the mux. Okay, now that resultant data is at our right data input. So to actually write it into our destination register, what does reg write have to be? 1. Right, and that's synchronous. So once this becomes 1, and then you get the next edge of the clock, that's when the actual data is stored into our destination register, which is 5 because our write address is right here.
Will the right data kind of like immediately like from a value for all these possibilities?
Will the right data? Oh, so you're talking about here?
Yeah, like the value, like the result that you get happens like instantly because you're only using buses and that becomes wrong.
Well, yeah, up to this point, but then for the actual storage to happen, you need the clock. But yeah, you're right. Up to this point, there's no like clock that's involved. Now, your question also brings up, a point I want to make. And it goes back to, why it's so important to make this mux simple. That's the ALU, right? See, if you use a single case statement for a mux, it's just gonna be a single thing. It's just gonna be the single multiplexer with like one time delay, one propagation delay. Time it takes for the signal to go from the input to the output. If you use if statements for a mux, what Vivado will do when it synthesizes and creates the logic for it, it's gonna create a chain of circuitry. It's not just gonna be a single thing. It's gonna be multiple things that are in series. And the more things you have in a chain in series, the longer it takes for the signal to get through. Now, we're gonna talk about this in more detail in a future class. But right now, and actually, I did mention this last class because you needed it for one of the examples I was doing to show a delay. Remember we delayed for like a half a second? And at the time I said, most instructions take 2 clock cycles. Okay, there are some instructions that take 3 clock cycles, but most of them take 2 clock cycles. Hold on just a second. So again, we're going to talk about this in more detail later on, but for right now, it basically takes 1 clock cycle to get the instruction here. And then from the time that the instruction is available here at the output of this memory module to the time that the result gets written into the reg file, and also we haven't quite finished this yet, something has to happen over here. Well, that all has to happen in 1 clock cycle. So it's very important to make this ALU very simple, because if this ALU is something complicated, like a long chain of circuitry that takes a long time to get through, your adder is not going to have enough time to do what it has to do before the next instruction is available. Okay, and that's going to screw up the timing and it's not going to work. Okay, so it is very critical that you just use 1 case statement, 1 single mux for that ALU. If there's anything more complicated, chances are your adder is not going to have enough time to complete what it needs to complete in 2 cycles.
So I noticed that ALU is doing like a lot of arithmetic, but it like doesn't have a clock on it. How does all that happen so quickly?
Well, when I say things happen quickly, what I'm talking about is how long it takes a signal to go from the input to the output. And if you just have one thing, like you just have one, multiplexer, there's only 1 time delay from any input to the output, right? Because, this select line is going to choose just 1 input at a time. So it's just going through like 1 piece of circuitry, if you will. But if you have a chain of circuitry, like circuitry that's in series, which is what an if statement is going to give you. Well, then it just takes longer to go from an input to the output. So that's all I'm talking about when I say, time it takes. It doesn't really matter whether you're talking about like a sequential circuit or a combinational circuit. The more circuitry you have, the longer it's going to take that signal to get through it.
I was just wondering how they modeled like addition. Is that a register? Is that like?
Well, in CP133, you remember the circuit that, we use it to first teach structural modeling, right? It's made out of multiple adders, right? Does anybody remember what that's called? It has a name.
Ripple carry adder?
Yeah, full adder is a part of it, but the whole thing together to add multiple bits is the ripple carry adder. Well, we teach that in 133 because, it's an intro class and it's a good example to use for structural modeling, right? Because you got to come up with the half adder and then the full adder and connect them all together. But there's more efficient ways of adding. And that's what the ALU is going to be, because we're letting the software do it for us. You could have like some sort of RCA circuit doing this addition for you, but it's going to be clunky, it's going to take a lot of time, and it's not going to work in this audit. Okay, so yeah, we're letting the synthesizer. So, when you design this and you run it and simulate it, you can look at the elaborated design and see, what it's produced, to do the addition as well as all the other functions. Okay, we're not done yet, because also what has to happen is we have to get the next, ready for the next instruction to be executed. So like we said, all the instructions are separated by 4 in address. So we take the previous address, right, that's been executed, we increment it by 4, we bring it over to this mux. So, assuming we're not doing any jumping or branching, we're going to talk about branching next class, and that's where we'll talk about what this piece of hardware does, the branch address generator. and also what this piece of hardware does, the branch condition generator. So we're not doing any jumping or branching, so we want this next instruction to be the next one that's in memory, you know, four-way an address from the previous one. So what would we want PC source, the select line of this mux to be? 0. Right, because this next address is at input 0 of the mux. So now that next address that's 4-way from the one we just executed is here at the input of the register part of the program counter. So now to get this at the output, what does PC write have to be? A 1. Okay, so you see this would be the complete data path and control signal. You know, the data path is in red, the control signals are in blue. Again, your control signals that are controlling the muxes come from the control unit decoder. The control unit, or excuse me, the writes and the reads, those are coming from the control unit FSM.
Since reset takes priority with the have to be 0.
Right, yeah. Yeah, if you want to write, yeah, preset's gotta be 0, or reset's gotta be 0. You'll see that after we do an initial reset at the very beginning, and again, that's going to occur in the FSM, there'll be like this initial state where we reset everything at the beginning. After that, you know, we just keep it 0. All right, so any questions about this instruction? Okay, because if everybody's good with this, I'm gonna erase what's in blue and red before we do the next instruction. All right, so if I miss anything in blue or red, let me know. I tend to miss something when I do this. I'll try to get it. Where I like to have like a whiteboard all clear.
Couldn't you also just like project the computer onto the board?
The trouble with that is it's usually like a bright spot when I use the projector and it's harder to see. Yeah, there's probably another way to do this better, but I haven't figured it out yet. Actually, I need a black marker here. Where'd my black marker go? Oh, it's over there. Okay, we'll leave this, we'll leave Dr. Hummel, we'll leave this, we just want to get rid of the red lines. The blue numbers. Did I miss anything? Anything blue or red?
3 and 1.
Oh, yeah, I always forget those. I was forgetting those in my other classes too. Is that it? I think that's it. Okay, so ready for the next instruction? We'll do 2 more instructions and take a break and then do the rest after the break. Okay, what does this instruction do? SLL. All right, that's a shift left logic. Let's find it in our description. Logical shift left. So what is this instruction going to do?
Going to perform a bit shift by the number of bits specified in 2, I believe.
When you say 2, you mean RS2,
Contents of register 2.
which is what in this? Like, where's RS2 here?
It's the 3rd one.
Yeah, so this is RS2. Where's RD? Where's the destination register? That's fine. So that means this is RS. Okay, so finish what you were saying.
Oh, I was gonna say it stores, or no. It takes the contents of register 12 and bit shifts it by the amount specified by the contents in register 15 and stores that in register 6.
You got it. Yep. So it's going to take the contents here, shift it by this amount, and put the result here. Okay. All right. So let's see how the data traces here. So we're going to start again with the address of the instruction. Okay. So what does this read enable have to be to get the instruction here? Got to be a 1. So now we have the instruction at the output of our memory module. It goes to the reg file. It gets parsed up, right? And because we have a source one, a source two, and a destination, that means we do have data at address one, we do have data at address two, we do have data at the right address. Is anything important about the immediate generator here? No, there's no immediate in the instruction, so it's not gonna matter. So what data do we have here at address one? What number is gonna be there? 12. How about for address two, what data? 15. How about for the right address? 6. Okay, what's gonna be at the output of RS1? Contents of register 12. What's gonna be at the output of RS2? Contents of register 15. Okay, this data is gonna come over to this mux. This data is gonna come over to this mux. What does this value have to be to get the data to the input of the ALU? It's gotta be a 0. What does this ALU source B have to be to get the data to the mux? A 0. Now we want a shift left to happen. So what does this one have to be? Yeah, a binary 1. Okay, now the Erlog symbol for a shift left is just 2 less than symbols like this. That means shift left. Okay, so the shift left happens. Oh, I should have put that in red. Okay, the shift left happens in the ALU. And then the result of that shift left is going to be at the output of the ALU. That's going to go up over here to this mux. What does this select have to be? A 3. Good. That puts the data on the right data input. So what does reg write have to be in order to store it in our destination register? A 1, yep. Okay, so that puts our result in the destination register. And then again, we got to get ready for the next instruction. So we're going to increment our address by 4, right? Where the next instruction is in memory. What does PC source have to be? 0. That's going to put that new address at the input of the register part of our program counter. So they actually write it to the output. We need this to be a 1. Okay, so does everybody follow that? Again, these are on Canvas, so you can see the result, you know, the red and the blue on Canvas.
It's not really related to this, but what is the line that goes from like the after the or adder that goes back to the top?
Oh, you're talking about this line here?
Yeah.
Yeah, that's not involved with any of these instructions, but we will get to a point where we'll see where this matters. It's just too early really to go over it because we don't know enough yet. But we will eventually talk about that. I just put it there for completeness, just to show that that 0 input does go somewhere. Okay, so any questions on this instruction before I erase? Okay, like I said, we'll do one more, then take a break. So erase all the blue and red again. Right. I won't forget names of them. Bless you. Bless you. All right, so we're almost ready. I think I got all of them. Did I miss any? I think I got all of them. Okay, one more before the break. All right, what does this instruction do? You got it, right. That's the add immediate instruction. So it's going to take that immediate, add it to what's in this register here, and then put the result here. Right, so this is our RD. This is our immediate. And I think this is RS1. Is this RS1? Okay, RS1. Okay, so notice this is the first instruction that we're doing the data path for that has an immediate. Okay, these other ones didn't have immediates. Okay, but just like the previous ones, we're going to start where the address of the instruction to be executed is. So, got this. So again, what do we need the read enable to be in order to get the instruction to be here? A 1. So now we have the instruction at the output of our memory module. Do we have relevant data at this input address 1?
Yes.
Yep, because what is it going to be? What number? What number? 2. Those will be 2. Does this input matter? No, because we don't have any source 2 in this instruction. So again, there's going to be data there, but we don't care. We're not going to use it. Okay, how about at the right address input? 9, right? We've got a destination register. 1929. Okay, this has an immediate, so now this does matter. Okay, we care about the immediate generator here because that instruction has an immediate. Now, notice that, again, the instruction is 32 bits, but at the input of this immediate generator, we're only using 25 of those 32 bits. See, we're just using bits 7 through 31. We're not using bits 0 through 6, right? We're not using those 7 most least significant bits 0 through 6. And what do those 7 bits represent in our machine code, the last 7 bits? Because you had to look at that for one of the previous assignments. Right, that's the opcode. So you see the immediate generator doesn't use the opcode to generate these immediate values. It only uses these 25 bits. So it takes these 25 bits and it makes it into 32-bit immediates. And again, the way it's formatted is what's on that handout, right? Like each type of immediate has a different format. And again, we'll go over, what you'll need from CP133 to actually create those different immediates in Verilog. We'll get there, okay, after the break. All right, but let's finish this example here. So we have a source register 1, so that matters. So here we're going to have the contents of register 2. Now, there's 5 different immediates, right? U type, I type, S type, B type, J type. What kind of immediate does the add I instruction have? Where do you suppose you would look to see where to get that information?
The assembly.
Yeah, in the assembly manual, right? That has all the instructions. Okay, so that means the data is being treated as a signed number. But do you see anywhere in the description where it tells you what type of immediate?
I type instruction.
That's true. Now let's see. Not all I-type instructions have immediates. And I'm not sure if all I-type instructions have I immediates. They probably do, but I don't know 100%. I'd have to look. But what if you look at the detailed description of the instruction? Is anybody looking at that page? Yeah, that one. Can you see there where it tells you what immediate we have? Look down by where the machine code is. Nobody sees it?
0 to BC. No.
Is everybody looking at this?
I.
I type, yeah, because you see where the machine code is, the instruction format, right underneath in parentheses, it tells you I type. Okay, so it's an I type immediate. That means that immediate 100, it's going to be at our I output, I type output of our immediate generator. Whoops, I'm doing the wrong color. God. Want data in red. Okay, so right here, that's where the 100 immediate is going to be. Okay, so what do we need this select to be to get the contents of register 2 to the ALU? Gonna be what? 0, right? That's gonna put this data as the input of the ALU. What does this must have to be to get the immediate 100 to this input of the ALU? It's gotta be a 1. Okay, so now, the add is gonna happen, and the add will happen in the ALU, provided that this ALU fund is equal to what? Right, you gotta look at our table over there, for it to add, the ALU needs to select to be a binary 0. Okay, so it's gonna take those two, add them together, put the result here at the output. That data is gonna come over to this mux. What does this have to be? A 3. Now that result is gonna be at the WD input, ready to be written into our destination register, but for that to happen, what does this reg write have to be? A 1. Okay, so now our result is stored in our destination register, but again, you gotta get ready for the next instruction. So we implement that address that we just, of the instruction we just executed, we increment that by 4. What does PC source have to be? 0. That puts the next instruction address at the input of our register part of our program counter. So for it to actually write to the output, we need the right PC write to be a 1. Okay? So you're seeing some redundancy here, huh? It'll start to get a little bit different when we do the next 2 instructions. But before we do the next 2, why don't we take a 5-minute break? And when you come back, we'll finish this. I'll talk some more about what you have to do in Verilog for the ALU immediate generator, and then you can do the activity and start on the assignment. Did you have a question?
Yeah, it was just about the generator. If we're assigning the same input to all 5 outputs, what's the need for 5 inputs?
Well, you see, if you look at the if you look at this handout, do you have this handout? I put one at every seat. See, if you look at this handout, see there's like 5 different immediates, and how they're formatted is different. See, like the I immediate, you're taking the 31st bit and you're replicating it 20 times and then attaching it to these 5 bits and then attaching it to these 5 bits. But then like the next immediate, you know, you're still replicating the 31st bit, 20 times, but then you've got a different set of bits here at the very end. And then these are quite different than those top 2.
Yeah, but we're only gonna have one immediate at a time, so why couldn't we just have one output and then connect it to all of the?
Okay, well, if you had one output for your immediate generator and there's 5 different types, you'd have to do something like in a series fashion. And that's gonna slow things up. And also the code that you would need in Verilog would be more complicated than just 5 assign statements. See, that's the real value of having things in parallel. It's faster and then it's easier to code also in your Verilog. So those are the advantages. Now, that's not to say, you know, it could be designed like that. It just, for our purposes, wouldn't be very good for what we need. Yeah. Did you have a question?
So I don't usually think of that. So is it like this 32 different places like the value of the data? Right. And then those 32 things are right. And then our register is or how is WDA work?
They're separate things. This is the address for the first source register. This is the address for the second source register, right? So that's where we're putting things that we're gonna operate on somehow. And then WA, that's the address of the destination register. That's where the result is gonna go. So the contents of these registers is what we're taking and either adding or subtracting or doing whatever operation. And then the result gets stored here in the destination register. And these are all addresses and, you know, here's the address for source one, here's the address for source two, here's the address for the destination. Okay. Let me start, and if you still have questions, I can answer after I finish. Okay, so let's go ahead and finish these last two instructions. So let's look at this one here, SLTI. What kind of instruction is that? It's not a shift. It's a word, that's true. But what's SLTI? Yeah, there's the word, set. It's set less than immediate. So what does that mean? You wanna-
Like a one, thing in the register was.
Right, yeah, we're doing a comparison, and we're gonna store a one in the destination register if that comparison is one way, right? And if it's the other way, we're gonna store a zero. But again, to see specifically what it does, if you read the description under the instruction, it says SLTI instruction compares the value of the source register RS1 with the intermediate value. If the value in the source register is less than the intermediate, the destination register is loaded a one, otherwise it's loaded a zero. Okay, so which one's our destination register? 8. And this is our source register, which I think is RS1, right? Usually when there's just one source register, it's RS1. I don't know if there's ever a case where it's RS2. Again, I haven't memorized all these instructions. Okay, and this is our immediate. Okay, what type of immediate do we have for this instruction? Yeah, it's an I type again. Yeah. Did you get that right from the description?
Yeah.
All right, very good. Okay, so we're gonna start. Oh, I didn't erase the data from the last. I'm sorry. I usually do that during the break, but I just forgot it. So sorry about that. But let's do it now. Erase all this. Get rid of all the red lines. Get rid of all this. Get rid of all this. This. Okay, did I get everything? Do you see any red lines or? Oh, I always forget those, don't I? Okay, I think that's it, right? Okay, so now, just like before, we start where the instruction, or excuse me, the address of the next instruction be executed is at right there. So what does this enable have to be? A 1. Okay, and then we're gonna have the instruction here, output DL1. Now, we have a source 1, so this address matters. And what's the data gonna be on this address? 20. Does the data on this input matter? No, we don't have a source 2, we don't care. Okay, but we have a destination register. So what data is gonna be here at this address? 8. And we also have an immediate, so we care about what's going to the immediate generator. So what are we gonna have at the output of RS1? Contents of register 20, right? What are we gonna have at the output of RS2? Something, but we don't care, right? Because we're not using RS2. There's gonna be some data there, but we're not gonna use it. Okay, but now we have an I immediate, so at the output of this I type of our immediate generator, we're gonna have that number 50. And then this data goes here. So what do we want ALU source A to be? 0. Okay, that's gonna put the contents of register 20 right at the input of our ALU. What do we want this select to be? 1. A 1. That's gonna put the I type at the other input of our ALU, and now the ALU is gonna do the set. Okay, so we look at our table here with the opcodes in our AL fun art. So what are we gonna have at our AL fun? Which one? Yep, the binary 2, this one here. See, notice you have a set less than and a set less than unsigned, right? So this one evaluates the numbers as unsigned, this one evaluates the numbers as signed. And now, the notation that's used to distinguish a set from just a less than is we use the less than symbol, but then we put a little s just to mean that it's a set. Okay, so that happens, and the result goes over here. So what does this select line have to be? A 3. That's gonna put the result data right at WD. And now to actually write it into the destination register, this read write has to be a 1. Okay, so that puts our result in our destination register. But again, to finish it, we take that address that we just executed the instruction for, we increment it by 4. And to use that now, what does the PC source have to be? 0. Okay, so again, now we have that next address. We have it here at the input of this red part of the PC program counter. So what does PC write have to be? A 1. Okay, any questions on that one? All right, we got one more to go. Did this one, now we have to do this one here. So let's erase what we have.
These are all on campus.
Correct, yeah. All the red and blue I've been drawing for each instruction, I have it on Canvas, they're in colors, so. Yeah, if there's anything you want to go over again or anything you missed. And you know, I'm making a video of this too. I don't know how well the red and blue is going to show up in the videos. You're also going to do, you know, a couple more instructions as an activity. So if there's something that's still not quite making sense, maybe the activity will help with that. All right, I think, did I get all the red and blue? Except for what I'm doing now.
Forgot that one.
Did I forget one? No. Did I get them all? All right, so this last one. Okay, what does this mean? What does LUI stand for? Yeah, it's load upper immediate. Now, I don't think we've ever run across this instruction by itself, but this load upper immediate, it's part of the load immediate command, right? Remember, we've used the LI load immediate, and load immediate, well, it can be a single real instruction, but it can also be 2 real instructions where it's a load upper immediate along with an add I. Okay, it just depends on how big the number your data is, whether it's just the single real or the double real. But anyway, when it's a double real, it's using the LUI along with that add I, okay, the load immediate pseudo instruction. But what the LUI stands for is load upper immediate, and what it does, it loads an immediate value into the destination register. The immediate value is left shifted 12-bit locations, and the lower 12 bits are cleared, made 0, in other words, before loading the destination register. So do we have an RS1 or RS2? No, we just have a destination register. This is the destination register, this is the immediate. Okay, so let's trace the data. So again, we start with the address of the instruction. This read enable has to be what? 1. We have the instruction here at the output of our memory module, our DL1 output. Do we care about the data here? No, there's no RS1. Do we care about the data here? No, there's no RS2. We do care about the data at the right address because we have a destination register. We do care about the immediate generator because we do have an immediate. Now, what type of immediate does this instruction have? Yeah, it's a U type. U type. Now, here's a key point. The 12-bit shift, right? Because this instruction shifts, it shifts the immediate 12 bits. That happens here. When you design this immediate generator, you're going to make that 12-bit left shift happen. Okay, so that 12-bit shift happens, it happens in the immediate generator. So it's the U type. You can see the U type output of the immediate generator goes up to this mux. So what do we need this select line to be to get that data to the input of the ALU? We need it to be a 1. So that's going to put that shifted data, that shifted immediate right there. What does ALU source B have to be? We don't care, right? There's nothing here that we need. So it can be anything. It's not going to be used. Now, ALU fun. Look at what we have over here for operations. We don't have an LUI by itself, but we have this LUI copy. So that's what we want ALU fun to be, and I'll explain why the copy is. Okay, so we want the ALU fun to be a binary 9. And you see the reason why you see the copy next to the LUI is because since the shifting has already occurred before the data gets to the ALU, all the ALU has to do is connect that input where the shifted data is to the output. So this is just an equal. Right? You just make the output equal to what's on this input because it's already been shifted. Okay, so now we take that shifted result and we want to put it into a destination register. So what does this select have to be? A 3. A 3. Okay, the data is now here at the right data input. So to write it into the register, we need this to be a 1. Okay, that puts the result into our destination register. We forgot to put the data here. What's the data on the address here? 7. So we're putting it into register 7. And then again, to finish it, we got to increment our program counter by 4 in address. The PC source has to be 0. And then PC write has to be what? 1. Okay? So that's this instruction. Okay, so once I go over, some more information that you need for modeling both the ALU and the media generator in Verilog or System Verilog, I just want to point out that the activity that you'll do as a group, groups being at a table, is doing the data, the red, and the control, the blue, for these 2 instructions. Now, what you should find out is that the data path and the control signals that you need for this AND instruction is a lot like one of the ones we did. It's a lot like one of those 5. In fact, it's the same exact thing except one thing's different. And same thing here for this 4 immediate. It's a lot like one of the 5 we did. In fact, it's the same exact thing except one thing's different. Okay, so even though there's 30 real instruction, about 30, maybe a little bit more, that you have to do diagrams for, what you'll find out is that there'll be a bunch of them, maybe a half dozen or more, that are essentially the same diagram. Okay, so that's some good news, right? kind of lessens the work some. All right, but the next thing here, before you can do the activity and also start working on hardware 4, is let's talk a little bit more about how you're going to model the ALU and also the media generator in Verilog. So we already talked about that. You want to make it a single case statement in its combination, right? Because there's no flaw. Also, when you do these functions, you just use the Verilog symbol for those functions. Like again, we mentioned this during the class. You're not going to like design an RCA to do the adding. You're just going to let the synthesizer do the work for you. So you're just going to use a plus sign. You're just going to add the two inputs together. So at one of these inputs of this mux, that the 0 input here, you're just going to have source A plus source B. That's what this input will be. Those two inputs added together. And then for the subtract, you'll just have one of the inputs minus the other input. Okay, do you remember the Verilog symbol for OR function? The vertical line. Okay, how about for the AND function? The little ampersand. Yeah, the ampersand like that. How about exclusive OR? I don't remember exclusive OR, what symbol that is.
Oh, it's the big arrow.
I was gonna say, what can you get by? For shift right logical, it's just two arrows like that, pointing to the right. For shift left logical, it's two going the other way, pointing to the left. Now, I mentioned this in a previous class, this SRA. What does that stand for? Shift right what? Arithmetic. Yeah, this is shift right arithmetic. And we'll talk about the difference between shift right arithmetic and shift right logic in just a minute. But in Verilog, the symbol that you use for the shift right arithmetic is just 3 greater than in a row instead of 2. Okay, then we have set less than, so that's just going to be a less than. Set less than unsigned, again, just less than. It's just treating the values as signed, the other one's treating as unsigned. And then for the ALU copy, the one we just did, well, like we talked about, since at the input, the data's already been shifted by the 12 bits in the immediate generator, you're just going to use an equal sign. You're just going to set the output equal to source A. Okay, so you're just going to have, these 11 inputs, going into your mux, and you're just using these symbols to do the operation on those inputs, source A and source B. So it's as though this mux is like inside this symbol. Okay, and again, the ALU fun is what's selecting which operation is going to be done. You have a question?
How do we see if it's unsigned or not?
Okay, that's the next thing.
Oh.
In System Verilog and also Verilog, it defaults to unsigned. Okay, so if you just leave it source A or source B when you're adding, subtracting, or any of these mathematical operations, it's going to treat those inputs as unsigned values because that's the default. But what you can do if you wanted to treat it as a signed value instead of an unsigned is you can do this. You put $sign, and then you put the word signed, and then you put in parentheses what input you want it to treat as signed. So you can just put like source A. Okay, so now that input source A, it's going to be treated as signed instead of unsigned. Okay. Let's see, what else do I got to talk about? Oh, let's talk about the difference between shift right logic and shift right arithmetic. I think I did this in a previous class, but let's do it again. I think the best way to explain it is just with an example. So if we have 1, 0, 0, 0 to start with, if we do a shift right logic, it's going to shift the bits to the right and replace the vacated bits with a 0. So if we did 1 shift right logic on this data here, this 1, 0, 0, 0, we would get 0, 1, 0. In fact, that's what you were doing in order to divide by 2. Remember we talked about dividing by a whole number, power of 2. And if you shift right one place and you replace the vacated bit with 0, that's divided by 2. All right, so that's shift right logic. Shift right arithmetic. Okay, starting with this data again. What's going to happen is it's still going to shift to the right, but it uses the most significant bit as the bit that it replaces the vacated bit with. So what we would get starting with this, with the shift right arithmetic, is you get 1, 1, 0, 0. Right? Because it still shifts to a 1, 0, 0, but now instead of putting a 0 to the vacated bit, it puts a 1 since that's what the most significant bit was.
So is the use for arithmetic that it like works with signs?
Exactly, because what is this number as a 2's complement?
Negative.
It's negative what? Negative 8, right? Because this is the sign bit, it tells us it's negative, then how do we get the magnitude of a 2's complement negative number? You flip the bits and add 1, right? So you get 0, 1, 1, 1 plus 1 is 1, 0, 0, 0, so minus 8. Oops, that's an 8. Okay, minus 8. All right, now what is this as a 2's complement number? Minus 4. Right, so you're exactly right. You would use the shift right arithmetic if you're dealing with time. Okay. Now notice there is no shift left arithmetic, right? It's only a shift left logic. Why is there no shift left arithmetic? Yeah, there's no, the most significant bit is the sign bit, not the least significant, right? If you're shifting this way, right, it doesn't make sense to have an arithmetic this way, right? Because the sign bit is the most significant bit, right? Not the least significant. Okay, so that's the reason you don't see a shift left arithmetic. Okay. All right, so let's see. I talked about single case statement, and I gave you the symbols and how to make something signed instead of unsigned. We talked about SRO and SRA. So any questions about the MUX before we move on to the immediate generator? Because this should be enough where you can model this now, either system Verilog or Verilog. All right, the immediate generator. Like I said earlier, it's generating these immediate values in parallel. So that's why you can just use 5 assignments. You know, you'll have an assignment for each of these types. And again, notice that we're not using all 32 bits. Right, we're using 25 of the 32 bits because if you look here, we're using all the bits except for the opcode bits. Now, to generate the immediates for the different types, this is where this sheet comes in handy, right? Because if you look at the I type immediate, for example, what this block here that you see where it says IR stands for instruction. So this first block, it's taking the 31st bit of the instruction and it's replicating it 20 times. It's making all these bits, whatever that bit is equal to. And then it's attaching to that bits 30 through 25, and then it's attaching to that bits 24 through 20. So you see, each one of these immediates is 32 bits. And it's creating it from these 25 bits. So clearly, because we got more bits going out than what's coming in, we're going to have some sort of replication. And you'll see all of these have some sort of replication. Okay. So from your CPE 133, the things you need, and let's say as an example, say I have some, signal IR, and it's declared the following way. It's declared as, 32 bits, 31 to 0. Okay, that's how it's declared, at the top of our module, you're declaring your inputs and outputs. Well, if you just want to use some of the bits, not all of the bits of these 32. You know, you can do something like this, right? You can just put like 7 to 4 IR. Right, and it's gonna take 4 bits of this 32 bits, right? It's gonna take bits 7, 6, 5, and 4. Right, so that's called parsing the bits. Right, you can see when you look at the formats for these different type of medias, you can see that you're doing parsing, right? You're taking certain bits. Okay, also in CP133, you did concatenation. I cannot spell this without looking, so this would be a good spelling word, I think. So for example, you can do something like this where, you know, say you have some output and you want to take, and you use braces when you do concatenation. So say we want to take, you know, these 11 bits, you know, from 20 to 10 and attach them to, you know, these 5. Okay, so to concatenate, which is just combining things, you use braces. So, and then you separate, you know, what you're connecting together with a comma. So it's just gonna take these 11 bits and attach it to these 5 bits. So you end up with a 16-bit signal. You have a question?
So if you're like attaching one bit to like 10 bits, are you gonna have to write that same thing over and over again 10 times?
No, that's the next thing, replication. So very good, thanks for the save. Yeah, replication. You can do this. Like say you have a single bit that you want to repeat 12 times. You can just do this. You just put the 12. And inside the braces, you would just put the bit that you want to replicate. Okay, so this would take whatever this bit is and just replicate it 12 times. Or if you had a value, like say you wanted to do 12 zeros in a row, you could just put inside the braces, you could just put 1 tick mark B 0, and that would take that 0 and just multiply it 12 times basically. Okay, so with using replication, concatenation, and the parsing of the bits, that's how you generate these various immediates. Right? You're just gonna have like, you know, type I immediate, however you want to abbreviate that. You know, assign to or assign whatever you call that output to something that looks like this. Did you have a question? I'll take your question next. What's your question?
Can you replicate more than one thing at a time?
Can you replicate what?
More than one thing at a time?
Yeah, like if you were to put like a range, you know, like if you were to put IR 4 to 0, it should take those 5 bits and then replicate it 12 times. So yeah, you can do that. You can also attach these, like, you know, you could put this inside here and, you know, have replication and attach to this and attach to this. So you can combine these. Now, when you combine them, sometimes it's a little funky what the braces have to be, like how many you need. So sometimes that's a little tricky.
So would it be like braces, then 12 braces,
I think,
braces, comma?
yeah, I think when you put this in as another one, you have to add like a couple of braces, but to tell you the truth, I have to look at what I don't remember from there. But, you know, again, Verilog will tell you if they don't like it, you know, like it all will tell you. You have a question? Let me take this question. You've been waiting and now I'll come back.
Okay, so you're gonna have braces, instead of braces.
Yeah, you could have something where there's like 2 braces in a row. That's what you're saying.
Alright, and then, secondly, the immediate generator, we know what type of media is based off of the opcode, right?
Well, that's true, but you don't have to worry about that here. I mean, that's something that, like the opcode and how it relates to the different instructions, that's gonna be really important when we get to the control unit. But here, it's literally gonna be just 5 assign statements. Like you don't need, you know, assign statements don't go inside blocks. So, you know, you don't need an always FF or an always com or.
Oh, so you just don't care. You don't need to make you don't need to make it like a box or change it.
No, it's just gonna be 5 assign statements, yeah. Yeah, and again, this is just gonna be a single case statement. And again, this would go in an always home. Cases have to go within blocks.
So with this data out exercise, like immediate generator doesn't like inherently know which ones send, oh, because the control unit is the one that decides, so they're all being generated into the mux, and then you use the decoder basically to select it, and that decoder will figure out later.
Right, exactly. All the muxes are controlled by the control unit decoder, and all the read writes are controlled by the control unit FSM. So yeah, you know, the reason I went over the data path and control today for different instructions is because I didn't want to wait right before you had to do the control unit, because then you would have to do like 30 of these all in a short amount of time. What I'm hoping is that, you know, I did these for you, you're gonna do these two, you know, as a group in an activity. Hopefully you'll see that, hey, this is a lot like one we did, this is a lot like one we did. And in fact, there's probably like 5 others that are a lot like this and 5 others that are a lot like this. So at least then it starts to get narrowed down, you know, instead of like 30 after today, maybe there's like 15 that, you know, are different than what we've done, you know, a lot different. But then, you know, on Thursday of this week, we're going to talk about branching, and we're going to go over the data path and control for the branch instructions, right? There's like 6 real ones, and we'll do, I think we do all of them on Thursday. So you'll have some more there. But, you know, eventually there's going to be some that we don't do in class, but hopefully by going through these exercises, you'll know enough where you can figure it out yourself for the ones, you know, we don't specifically go over in class. But eventually you will need all of these to do the control unit.
So there's no submitting this, it's just having for our own.
Well, no, this is graded that I do want each table, each group to submit one diagram for this instruction and one diagram for this. So each table will turn in 2 diagrams, one for the and the other one for the or I. Yeah, and it's very lenient grading. As long as I see that you've gotten it correct, it'll just be like a check you did it. Again, my main, you know, there's a method to my madness here. I'm hoping that by doing this early, you're not going to wait till right before you got to do the control unit to do all this, that you'll have most of it at least. And maybe you got to do a few more when you're ready for the control unit in a few weeks. Okay, did you have an question?
Going back to the ALU mux, so are you supposed to treat all of them as signed unless it's the same
Okay.
that I'm done?
Okay, good question. The question is, in this mux here, are we supposed to treat all of these input assigned for all the operations? The quick answer is no. The way you find out is you look at the instruction, right? You look at the description. If the instruction says anything about 2's complement, it's got to be signed, right? Okay, so yeah, again, there's a method to my madness. You know, I want you to look at that instruction manual and figure out, you know, which ones have to be signed, which ones don't have to be signed. Right, that's just to get you familiar with the instruction manual. The more familiar you are with the instruction manual, the easier the control unit's going to be. Right, because half the battle of the control unit is recognizing patterns. You know, it's recognizing that, hey, these 10 or 12 instructions, they basically have all the same data path. There's only one thing that's different. You know, so that helps you with the coding for that. It's going to be a lot less than if you try to do every instruction as though it's unique. You know, if you try to do every instruction as though it's unique, you know, the code for your controller is going to be humongous. All right. So, you know, doing these diagrams, even though it might be some work in the short run, it saves you work in the long run. All right. So any other questions before you get started with the activity? Because the next thing to do is the activity. Every table has one diagram at this point. I'm going to come around with another diagram because you need 2, one for each instruction. Don't do both instructions on one diagram. Do separate diagrams for each instruction.